Hi guys, welcome back to Science with Ganesh. Today I'll be explaining IGCSE Chemistry, Organic Chemistry Part 2. So let's start. So this is the syllabus content 11.4 alkanes. So in this we'll be covering the everything about alkanes, their reactions, and that they are saturated hydrocarbons. So alkanes are a group of saturated hydrocarbons. Now, what does the word saturated hydrocarbon mean? It means that the word saturated means that alkanes have only single carbon-carbon bonds. And hydrocarbons, I have already told, hydrocarbons are compounds made of hydrogen and carbon only. And then alkanes are usually unreactive, but they do undergo combustion and substitution reactions. Now, alkanes undergo complete combustion to form carbon dioxide and water. So the example here is given CH4, which is methane. When it reacts with oxygen, it forms carbon dioxide and water. Okay. And now substitution reaction of alkanes, this is only included for extended students. So in a substitution reaction, what happens is that one of the hydrogen atom, it is replaced by a halogen. That halogen here we have taken as bromine. However, it could be chlorine, fluorine, or any other halogen. Now, this reaction takes place in the presence of ultraviolet radiation. This is why it is called a photochemical reaction. Now, UV radiation provides the activation energy required for this reaction to occur. And that's it about alkanes. Now we will do about alkenes. We'll look into their reactions, how they are produced, and that we will look into the fact that alkenes are unsaturated hydrocarbons. So alkenes are unsaturated hydrocarbons. As I told, alkanes are saturated, which means they have only carbon-carbon single bond. However, alkenes are unsaturated, which means they have carbon-carbon double bond. And so alkenes can be manufactured by cracking of longer chain alkanes using high temperature and powdered catalyst of alumina or silica. There's a mistake here. It doesn't need to be and silica. It needs to be or silica. So longer chain alkanes using higher temperatures and powdered catalyst of alumina or silica can produce alkenes. Now these cracking of these larger alkenes basically helps to produce shorter hydrocarbons, which ensures that the shorter hydrocarbons are more useful than the larger ones, and so we do the catalytic cracking of alkenes. Okay. And then bromine water test. So to differentiate between alkanes and alkenes, we use a bromine water test. Bromine water is basically an orange colored solution. When we shake it with an alkane, it will remain orange. However, if we shake it with a alkene, it will decolorize, and this reaction between alkenes and bromine is called an addition reaction. So what happens in this reaction is the double bond which is here between the two carbons is broken down, and each carbon forms a bond with bromine as well. So as you can see that the double bond is broken in the product and there is a bromine attached to each of the carbon. And then we have the addition reactions, which are included for extended students only. Now, alkenes undergo addition reaction in which atoms of a simple molecule add across the carbon-carbon double bond. As I showed in the previous slide, that the double bond is broken and the two carbons and alkene molecule, a simple atom is added across the carbon atom. Okay, now alkenes can undergo addition reaction with hydrogen, which is basically called hydrogenation, and it occurs at 150 degrees Celsius and a nickel catalyst. Now alkenes can also undergo addition reactions with steam, in which an alcohol will be produced. Now since water is being added to the molecule, it is called a hydration reaction. And the reaction is very important to produce alcohols, and the conditions required for the reaction is the temperature of 300 degrees Celsius, pressure of around 60 to 70 atmospheres, and a concentrated phosphoric acid catalyst. So this is the reaction I can show you. So this is in the first one, halogenation reaction, in which a halogen is added. So basically this double bond is broken down first, and then the bromine bromine atom is attached to each of the carbon atoms involved in the double bond. And then this is the hydrogenation reaction in which the hydrogen atom is added. So the alkene basically turns into an alkane and there is no double bond then. And in the steam, it forms an alcohol. So in the hydration reaction, it is forming an alcohol, and this is the water molecule is added to the alkene in the same way as the previous two reactions. Okay, now let's move on to alcohols. So this is the syllabus content 11.6. Now we can manufacture ethanol in two ways. First is the hydration of ethane with steam, like we discussed when we were learning about alkenes, and the second is the fermentation of glucose. Now when we are doing hydration of ethane, a mixture of ethene and steam is passed over a hot catalyst of phosphoric acid at a temperature of approximately 300 degrees Celsius, and the pressure used is 60 atmospheres. This is even mentioned in the previous slides when we were learning about the ethene addition reaction of ethenes. Okay, then when we are doing the fermentation of glucose, basically sugar or starch is dissolved in water and yeast is added, and the mixture is then fermented between 25 to 35 degrees Celsius with the absence of oxygen for a few days. So basically anaerobic respiration is basically fermentation of glucose. Now yeast contains enzymes that catalyze the breakdown of starch to or sugar to glucose. If the temperature is too low, the reaction rate will be too slow, and if it is too high, the enzymes will become denatured. So we need to maintain an optimum temperature, which would be around between 25 and 35 degrees Celsius. Now the yeast will respire anaerobically using the glucose to form ethanol and carbon dioxide, and the reaction is given C6H12O6, which is glucose. When it is respiring anaerobically, it is giving us carbon dioxide CO2 and C2H5OH, which is ethanol. So these are the two ways in which we can manufacture ethanol. Now combustion of alcohols, similarly as alkanes and alkenes, when alcohols are burnt in excess oxygen, they form CO2 and water, and the uses of ethanol are as a solvent and as a fuel. Now advantages and disadvantages of the manufacture of alcohol. Of the two ways, fermentation of glucose and the hydration of ethene. So there are advantages and disadvantages for both of the processes, and this is only included for the extended curriculum. So for the fermentation of glucose, the advantages are the renewable raw materials, as glucose is renewable. It's not ending, and then we don't need a very high temperature or a very high pressure for the fermentation of glucose, so it is not that expensive, and a very little amount of energy is required for the reaction. Now the disadvantages is that it is a stop-start process, which means that it only produces the alcohol in batches. It is not a continuous process, and a lot of workers are needed, and since it is not a continuous process, it means it's very slow. And fermentation of glucose, as I told you, it forms carbon dioxide and ethanol, so it is impure and we need to remove the carbon dioxide. And then the other method is the hydration of ethene. So hydration of ethene, it is a continuous process and a very few workers are needed. Since it is continuous, it is fast and only alcohol is produced, so it is a pure product. However, the raw materials which are used in the hydration of ethene, like ethene, so that is non-renewable, and a very high temperature and a pressure is used, and a lot of energy is needed for the reaction. And now let's move on to the next 11.7, which is carboxylic acid. So carboxylic acids behave like any other normal acid which you can take. They react with metals, bases, and carbonates. The salts formed by the reaction of carboxylic acids all end with anoid. So if we are taking an ethanoic acid, it will form ethanoid. If we are taking methanoic acid, it will form methanoid. and so on, propanoic acid, propanoid, and butanoic acid, butanoid. So reaction with metal, so here I have given an example of magnesium and ethanoic acid. It is forming the product magnesium ethanoid and hydrogen. When we react it with a base, which is potassium hydroxide and propanoic acid, we will get potassium propanoid and water. And now when we are reacting butanoic acid with potassium carbonate, we will get potassium butanoid and water and carbon dioxide. Formation of ethanoic acid, this is only for the extended students. So there are two methods used to make carboxylic acid. One is oxidation by fermentation and using oxidizing agents. So when we are doing oxidation by fermentation, the fermentation of alcohol will produce a weak solution of vinegar, which is ethanoic acid. This occurs when a bottle of wine is opened, as bacteria in the air will use atmospheric oxygen from air to oxidize the ethanol in the wine. And the reaction is given here, C2H5OH, which is your ethanol. When it reacts with oxygen, we will get ethanoic acid and water. Moving on to the next method, which is using the oxidizing agent. We can also use potassium manganate to produce carboxylic acid. So this involves heating the ethanol with acidified potassium manganate in the presence of an acid. So the heating is performed under reflux, and the point reflux here means that condensation of vapors, and that vapor is then brought back into the reaction system. So that is the word reflux meaning. The condenser prevents the volatile alcohol from escaping the reaction vessel, as alcohols have low boiling point. So the condenser will again condense the vapor of alcohol and bring it back into the reaction system. Okay, and the solution, when this reaction occurs, the solution changes from purple to colorless. So the reaction is CH3CH2OH, which is ethanol, and the oxygen here in brackets, it is basically the oxygen provided from the oxidizing agent. It represents the oxidizing agent, and it is forming ethanoic acid and water. Let's move on to the next slide. Esterification, this is only for the extended students. So alcohols and carboxylic acid, when they react together, they form esters, and this reaction is called esterification reaction. Now esters are compounds with the functional group RCOR, where R represents different carbon chains. Esters are sweet smelling oily liquids used in food flavorings and perfumes. Now, ethanoic acid will react with methanol in the presence of concentrated sulfuric acid to form methyl ethanoid. As you can see, I have put the reaction over here. Now we can see that the hydrogen from the OH of the methanol and the OH of COOH from the ethanoic acid, they react to form the water molecule, which is removed, and when it is removed, we'll get methyl ethanoid and water. Now this reaction can be reversed, so when we add water to methyl ethanoid, we can again get ethanoic acid and methanol. Okay, now we will move on to the last part of organic chemistry, which is polymers. So in polymers, each repeat unit is connected to the adjacent unit via covalent bonds. Polymers are basically made of many different monomers. Some polymers contain just one type of unit, which examples include polyethylene and polychloroethylene. And others can contain two or more different types of monomer units, and these are called copolymers. Examples include nylon and biological proteins. So we'll be learning about nylon and biological proteins in the upcoming slides. Now different linkages also exist depending on the monomers and the type of polymerization. Examples of linkages are covalent bonds, amide links, and ester links. Polyethylene is formed by the addition polymerization of ethene molecule. So as you can see in the ethene molecule, when ethene is polarized, when it is converted into polyethylene, it forms when it is converted into polyethylene, basically the double bond is broken here, and it is a reaction. It is called addition polymerization. So the double bond is broken, and then it forms bonds with the next adjacent ethene molecule, and we can get a long chain, and that is polyethylene. And this number n is because we will have n number of ethene molecules. We don't know how many can be there, so we instead represent it with the subscript n. Now addition polymers are formed by the joining up of many monomers and only occur in monomers that contain C double bond C. One of the bonds in each C double bond C bond breaks and forms a bond with the adjacent monomer, with the polymer being formed containing single bonds only. This is what I had said previously, like this ethene molecules forms the polyethylene, and the double bond is broken and each is forming a bond with the adjacent monomer. Now they might tell us to find the monomer. So here when we take this chain, we can understand that this ethene is the monomer of this polymer. So similarly, you need to see it would be a chain of many repeating units. So you need to take the one repeating unit, and that would be your monomer. And then the previous one which we did was addition polymers, and now we have condensation polymers. So condensation polymers are formed when two different monomers are linked together with the removal of a small molecule, and that small molecule is usually water. Now this is the key difference between addition polymers and condensation polymers. When we are doing addition polymerization, we have only a single product, which is your polymer. However, in condensation polymerization, we have a polymer being formed and a water molecule being formed. Now the monomers involved in the condensation polymerization have two functional groups present, one on each end. The functional groups at the ends of one monomer react with the functional group on the end of the other monomer, in so doing creating long chains of alternating monomers forming the polymer. Hydrolyzing, which is basically adding water to the compound in acidic conditions, usually reverses the reaction and produces the monomers by rupturing the peptide link formed between them. Okay, now we have nylon and PET. So basically we have polyamides and polyesters. Polyamides are formed from dicarboxylic acid and diamine. The example is nylon, and polyesters are formed from dicarboxylic acid and diol, which is example is PET. The full name of PET is not required for the IGCSE students. So nylon is a polyamide which is made from dicarboxylic acid and diamines, and then each COH group reacts with another NH2 group on another monomer. An amide linkage is formed within the subsequent loss of loss of one water molecule per link. So as we can see, this is your NH2 group and this is the COH group. The OH from the COH and H from the NH2 are removed, which basically forms your H2O molecule, and we have an amide linkage forming here. Okay, and let's move on to the next, which is forming the polyesters, which is PET. So the full name of PET is basically polyethylene terephthalate, which is not required for the IGCSE students. Okay, and it is a polymer made from dicarboxylic acid and diol. Now each COH group reacts with another OH group on another monomer, and an ester linkage is formed with the subsequent loss of one water molecule per link. So each link is going to give us a water molecule, and we can look, this is the OH part from which the H has been removed, and from the COH part OH has been removed, which forms one water molecule, and each linkage is therefore leading to the formation of one water molecule. Now PET can be converted back into the monomers and be repolymerized. It can be depolymerized either using enzymes or by chemical methods. Enzymes present in microbes break down the PET to the original monomers. The same can be achieved using solvents, a catalyst, and mild heating. Okay. Now plastics are formed from polymers, and there are non-biodegradable plastics which do not degrade over a time or take a very long time to degrade and cause significant pollution problems. So plastic waste has been spilling into the sea and the oceans, which is basically causing significant problems to the marine life. And in landfill sites, are quickly filled up due to the non-biodegradable plastics, as they cannot be broken down by any microorganisms. And polymers release a lot of heat energy when they are burned, and they produce carbon dioxide, which is a greenhouse gas that contributes to climate change. And if they are not burnt in enough oxygen, as in they go through incomplete combustion, they will be producing carbon monoxide, which is a toxic gas, and it reduces the capacity of the blood to carry oxygen. And now we have the last slide, which is proteins. Proteins are natural polyamides. Amino acids are small molecules containing NH2 and COH functional group. This is a general structure of an amino acid. The R here represents a CH3 group or any alkyl group. Each we have like 20 different amino acids. So each amino acid has a different R group, and this is how a protein structure will look like, and these are the amide linkages. So you can see there is this carboxylic acid group, and the OH has been removed, and from the amine group as well the hydrogen has been removed, forming a water molecule. These boxes represent different carbon chains, because each amino acid is different. Each amino acid has a different R group. So these boxes represent that it is a different amino acid. Thank you so much. This is the end of organic chemistry for IGCSE. For more such videos, please like, share, and subscribe to my channel. Thank you so much.